Okay, so this is my simplified version. Now I'm going to do a slightly more complicated version. We're going to actually look at it in the loop, if I can pull it off, okay? If I can pull it off. Okay?
Well, if you can pull it up, then how will
Yeah,
you pull it up?
we'll see. Okay, so here's my closed loop of DNA. I'm going to simplify it. This thing I call flower power. Other people call it Patrick, SpongeBob's friend. Okay. See, but I grew up in the 60s, so it was all about flower power. Oh, crap. Okay. Here's my nucleoid, and don't forget, it's got hydrogen bonds. I just get too lazy to draw them all the time. So the loops are held together with hydrogen bonds. Blah, 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 blah. Okay. DNA replication has to be initiated. First step is initiation. There's a lot of little details we could go into that your book goes into that we really don't have time to worry about. Because as a nurse, they're going to come to you and be like, you didn't write the first step of DNA replication down on your patient's chart. You're like, I don't remember what it is. It's initiation. Okay, so what's going to happen is this is going to replicate in two directions. It's going to replicate that way, and it's going to replicate that way. So in order to do that, the loop kind of has to open up. And how does the loop open up? The hydrogen bonds break. But it's temporary. They're weak attractive forces, easily formed, easily broken. So Patrick might look a little mushy for a while, if I can draw this in any meaningful way, whatever. So the loop opens. When the loop opens, that's because the hydrogen bonds break in the middle. Right? And the new chain strand of nucleotides is going to be pieced in here, and the other chain of nucleotides is going to be pieced in here and then stitched together, ligase together. So you'll have two strands. So by the time you're done, you're going to end up with you got the idea. Whatever. Probably created a mutation. Good one. Okay, so by the time it's done copying, right, one strand's going to be growing in one direction. That's a very messy strand, isn't it? And one's going to be growing in the other direction. And eventually, it's going to come around to the middle. When these strands are done, they start twisting up, back up again. So, we'll try to watch a little video clip, because I can't draw all that. My problem with the video clips is they're for eukaryotic DNA replication. They're not for prokaryotic DNA replication. And prokaryotic DNA replication is the same as eukaryotic DNA replication. But eukaryotes can have multiple chromosomes. Bacteria only have one nucleoid. And it happens right at that nucleoid without a nuclear membrane, without any dancing of chromosomes or any of that stuff, so it's just a little bit different. Question? Question? No question? No question. Okay, so I simplified it, and then I did it slightly more challenging. All right, for DNA replication, what do you need? You need the original DNA. That's what you're going to copy. That's what you're going to copy. Second thing, you're going to need enzymes. Enzymes are going to direct every step that happens. Enzymes are going to put new nucleotides into place for the new strands. Enzymes are going to proofread. Enzymes are going to stitch together the nucleotides. And enzymes are going to stitch together the Okazaki fragments for the side that's backstitched. All that stuff. So you're going to need a complex of enzymes. We're just going to lump it all into one enzyme name, and that is DNA polymerase. which is one of the enzymes. There are many more enzymes, so we'll just put DNA polymerase and a complex of enzymes. If you're curious, go to your textbook. It lists all the different enzymes the cell could possibly have and what they're named and what their jobs are. Quite frankly, in a 6-week class, we really don't have time for that, because then I wouldn't be able to tell you cat stories. All right, so DNA polymerase enzymes. And another thing you're gonna need is nucleotides, because it's a double-stranded chain of nucleotides. And if I'm gonna make 2 new strands, one for each copy, right, I'm gonna need more nucleotides to make the copies, right? We call those free nucleotides, which means available. If the cell is healthy, has good nutrition, it should be able to synthesize or make from foods that it's eaten all of the nucleotides that it needs. So we call those free or available nucleotides to build the new strands. Okay,
What about primer? Is it part of DNA polymerase complex?
the primer
Yeah.
is actually part of the sequence. Is that right, Colton? The primer is part of the sequence or part of an enzyme? Primer's part of a sequence, actually, I think. Maybe both. Who cares? Yeah, the primer starts at copy. All right, now, actually, the primer's more for protein synthesis, but anyway, so the reason they call it semi-conservative replication is because half of each new copy conserves the original DNA. So each new copy is half original and half new. It's semi-conservative. Each new copy conserves half of the original DNA. And what's the new copy? It's the daughter cell's nucleoid. Yeah. Okay, why? Why would a cell bother to have double-stranded DNA? One strand isn't enough to carry the genetic code? Why would it bother to have double-stranded DNA? And why would it conserve half of the original DNA?
Well, I think that it needs.
She literally answers all my questions. So cute. Yes, go ahead.
Well, okay. Why does it need a double strand? I think it's because, it has to store information. Because in this DNA, there's all of the information, so it has this double helix in order to, to make the DNA into smaller space, I think.
It has to store the information, but it has to pass it on to the next generation. So that's why. It has to pass it on to the next generation. So this is the way to do it. Anyways, let's go back to the olden days when I was in college. So when I was in college,